Hello everyone, this is lecture 70 of Principles of Electric Circuits. We will introduce filters. We know that noise is ubiquitous in nature. There are many ways to resist noise. In the previous lectures of this course, we have introduced that the digital system and the hysteresis comparators are effective methods for eliminating the influence of noise fundamentally. But sometimes we still bring in the noise to the system. In this case, we need filters. The so-called filter is the equivalent used to eliminate the influence of noise. The scope covered by filters are very broad. Here we give a simple introduction. If the useful signal frequency and the frequency of the noise are not overlapping, in this case, the designed filter is called the classical filter. If the filter implemented by using analog system is called an analog filter. If the analog filter is implemented by passive elements, it's called the passive filter. If it's implemented by active elements, it's called the active filter. If the classic filter is implemented by digital system, it's called a digital filter. Sometimes the frequency of the noise and the signal frequency are overlapped. In this case, we need to estimate the characteristic of the noise and then design a modern filter. Did you find? In order to eliminate the effects of noise, various types of filters were put forward. About the principle, design, and use of these filters, we will learn from different courses in the future. For example, passive filters will be taught in circuits and systems, and active filters will be taught in analog electronics and power electronics. Digital filters will be taught in digital signal processing. Modern filters will be taught in modern signal processing. It can be said that the learning process of electrical engineering field is the learning process of filters. In this course, we focus more on analog filters, so we divide analog filters more carefully. Firstly, if classified by function, it can be divided into 5 categories. The first kind is called a low-pass filter, LP for short. The second part is called high-pass filter, HP. The third part is called bandpass, BP. The fourth kind is band-stop filter or notch filter, BS. The fifth kind is called full-pass filter, FP. It is classified by function. In addition, it can be classified by the implementation elements. As I said before, the filter implemented by passive elements is called passive filter. The one implemented by active elements is called active filter. The so-called passive filter is a filter implemented by RC or LC. The so-called active filter is a filter implemented by operational amplifier or various kinds of power electronics switches. In this course, we will discuss more the passive and active filters constituted by RC, LC, and operational amplifiers. Next, we will carefully discuss the previous 5 kinds of filters. First, the filter is a signal processing device, which has input port and output port. We assume that the input port can connect the excitation and output port is the response. For a low-pass filter, as the name suggests, it should make the low-frequency signal pass and the high-frequency signal be attenuated. So the AF characteristic of the ideal low-pass filter should be like this. The frequency can be specified by the designer. We call it cut-off frequency. Similarly, for the high-pass filter, the low-frequency signal is attenuated and the high-frequency signal remains the same. The so-called bandpass filter refers that some frequency band signal can pass and the rest is attenuated. That is like this. The so-called band stop filter is in turn. That is, some frequency band signal is attenuated and the rest can pass. The so-called full pass filter refers that all frequency signal can pass with no attenuation. You might ask, why do we need a full pass filter? Here we only draw the AF characteristic. In fact, there is also PF characteristic of the filter. By adjusting the phase of input and output, the full-pass filter plays the role of adjusting signal. Here we ask you a question. If we have the low-pass filter and a high-pass filter, then how to get the band-pass filter and band-stop filter by combining them? Next, we give two examples. The analysis of its frequency characteristics has been taught in Lecture 69, that is to say, if we define UC as the output and US as the input, the transfer function of the circuit is like this. We draw the AF characteristic of the transfer function like this. Here we need to emphasize that 0 refers to 0 dB. According to the knowledge we taught in Lecture 69, dB equals 20 times log UO over UI. So 0 dB means UO over UI equals 1. We can see from the classification of filters we taught before, it's a low-pass filter, but it's not an ideal low-pass filter because with the increase of frequency, the amplitude of the transfer function attenuates gradually, so the cut-off frequency of the filter needs to be defined artificially. Generally speaking, we consider that a filter is cut off when the angular frequency is greater than 1 over RC. That is to say, when the amplitude frequency of the transfer function is less than -3 dB. Why? The -3 dB means that amplitude of the transfer function is 0.707. The RC 1 over RC is defined as a cut-off frequency, or known as a half-power frequency. Here we need to review what we taught in Lecture 69. We specifically introduced the 0.707 AF characteristic. Why is called the half-power frequency here? Look, 0.707 means that the ratio of the input and output is the reciprocal of the square root of 2. Then it means that the ratio of output power and the input power is 1 over 2. So there is a so-called half power. It means that the output power is less than half of the input power when the frequency is more than this value, and we think the whole filter is cut off.